Here, we need to find the limit as x approaches minus 2 of x to the third power minus 2x minus 1 over 3 minus x. So we're gonna go ahead and use direct substitution to evaluate this limit, since minus 2 is in the domain of this function. So to find the limit as x approaches minus 2 of x to the third power minus 2x minus 1 over 3 minus x, we're going to simplify, substitute minus 2 in for x. So we get minus 2 to the third power minus negative 4 minus 1 all over 3 minus negative 2. So let's simplify numerator. So we get minus 2 to the third power, which is minus 1 times 8. We get minus 8. And 4 plus minus 1 is 3. So we get minus 5. Now, in the denominator, we have 3 minus negative 2. So we end up with 5. So the limit as x approaches minus 2 of our function is minus 5 over 5. Simplify this to minus 1 if you need to. Now, once again, if the limit is in the domain of the function, then you can use direct substitution to evaluate the limit. Next problem. Find the limit as x approaches 3 of square root of x plus 1 over x. In this problem, we're going to use direct substitution to evaluate this limit. Now, the reason why we can use direct substitution is because 3 is in the domain of this function. So let's go ahead and plug in 3 in for x. So we get square root of 3 plus 1 over 3. Now the denominator is simply 3. So the limit of this function as x approaches 3 is 2 over 3. However, not all limits can be evaluated by direct substitution. Let's look at this example. Here, we want to find the limit as x approaches 5 over 2x squared minus 9x minus 5 over x minus 5. Now, if I try to do this using direct substitution and I plug the 3 in for the x, we can notice that I get a 0 in the denominator, and that's undefined. So 5 is not in the domain of our function, so we cannot use direct substitution. So we could do this by graphing, and we could do this by a table of values. But I still want to be able to do this in algebraic way. So what we want to do is we're going to solve this by factoring. So if you look at the numerator, we get 2x, and we get 1 and 5. And we get positive and negative. So 2x squared minus 9x minus 5 factors to 2x plus 1 times x minus 5. Now the denominator stays as x minus 5. Now, why does factoring help us? Well, what happens to the x minus 5 terms? Well, they cancel. This is what was giving us the issue when we were using direct substitution. So now I can find the limit as x approaches 5 of 2x plus 1. And now we can use direct substitution. So this equals 2 times 5 plus 1 is equal to 11. So the limit as x approaches 5 of our function is equal to 11. So we use factoring in this case. That factoring help us eliminate the term that was giving us the problem. And then we use direct substitution once again. Find the limit of h approaches 0 of 2 plus h squared h squared minus 3 times 2 plus h plus 2 all over h. In this problem, if we try to use direct substitution and plug in 0 in for h, we'll get 0 over 0, which is an indeterminate form. So to find the limit, we need to simplify this function, factor it. And the numerator, I'm going to multiply some of the terms to get rid of all these parentheses. When I evaluate 2 plus h squared, I get 4 h plus h squared. When I distribute the minus 3, I get negative 6 minus 3h, and I have this plus 2. And all of this is over h. Now, when I simplify the numerator by combining like terms, I end up with h squared plus h all over h. Over h. And once again, we'll still try to find the limit as h approaches 0. Now I can go ahead and factor the numerator. So we get h times the quantity h plus 1 all over h. And we have our h's canceling each other out. And remember, the h is what was causing our problem. So we have the limit as h approaches 0 of h plus 1. Now we can use direct substitution, plug in the 0 in for h, and we're left with 1. The limit as h approaches 0 of our original function is equal to 1. In this problem, we have the limit as x approaches 0 of the square root of x squared plus 4 minus 2 all over x squared. Now, we cannot find the limit by substituting, because when we plug in 0 in for x, we'll get a 0 in the denominator. Now, if we try to simplify this function, there's really nothing we can do. We cannot factor or combine like terms, so simplifying is not an option in this case. So we need another method. Next method we're going to learn about is called rationalizing the numerator. Rationalizing the numerator is when you multiply the numerator by the same expression, except that you change the operation between the square root and the constant term. In this case, we're going to multiply the numerator by square root x squared plus 4 plus 2. So here we have a subtraction sign, so you do the opposite sign. Now, if I multiply something to the numerator, I gotta multiply by the same amount in the denominator. And this is called rationalizing the numerator. So now we're gonna go ahead and multiply this out. So what we are really doing is we are multiplying two binomials. So when I multiply my two x squareds, they cancel out. So I'm left with x squared plus 4. Now when I multiply this term and 2, I'm left with the plus 2 times the square root of x squared plus 4. Now if I multiply negative 2 and the square root, I'm left with negative 2 times the square root of x squared plus 4. And I multiply my negative 2 times plus 2, which I get a minus negative 4. Now these two terms cancel each other out, so I'm left with x squared, and 4 also cancels each other out. So I am just left with x squared in the numerator. Now the denominator, I'm not really gonna multiply it out. I'm just gonna leave it as is. So I'm left with x squared times x squared plus 4 plus 2. And once again, we're checking the limit as x approaches 0. Now my x squared terms cancel each other out. So we're left with 1 over the square root of x squared plus 4 plus 2. And once again, we're trying to find the limit as x approaches 0. Now we can use direct substitution because I got rid of that x in the denominator that was causing a problem. So when I plug in 0 into our function, we get 1 over the square root of 0 plus 4 plus 2. So we're left with 1 over 4. So the limit of our original problem is 1 over 4. And we use rationalizing the numerator in this case because I could not factor and I cannot use direct substitution. Thank you for watching.